Hi, and welcome to another online lecture for General Physics 2. This lecture is dealing with the topic of waves and wave reflection, and it is the first lecture in our fourth and final unit on waves and optics. In my experience, people have varying exposures to the topic of waves in their General Physics 1 classes. Some people have addressed them in class, some have not. So for those of you that have seen wave physics before, my apologies for the redundancy, but for those of us that haven't, we need a few ideas about how waves interact with one another in order to make predictions about the behavior of light. So we're going to do a few activities regarding waves here at the beginning before we transition into thinking about how light behaves. So what is a wave? Well, a wave is, broadly speaking, a traveling disturbance. It carries energy from one place to another place, but it does not carry the material itself from one place to another place. So the wave is transmitted through the material, but the material itself stays rather localized. In this picture there are water waves, and though they crash over and over and over again on the beach, the entire water that's in the ocean does not eventually pile up on the beach. In fact, the level of water remains relatively the same. If you think about listening to sound waves when someone is speaking or singing or something like that, you can hear the sound, and that's indicative of the sound wave entering your ear, but the medium that the sound wave is traveling through, the air itself, doesn't go in your ear. You don't feel a wind when you're listening to somebody speak. Their breath does not travel across the room and enter your ear. Rather, the wave just propagates through the air that is in the room and leaves the air particles relatively undisturbed after it's passed through. There are two broad categories of waves, and if you did the exploratory lab at the beginning of this unit, you should have observed both of these types. Type 1 is a transverse wave, and you get a transverse wave by, if you have a stretched out slinky, shaking the slinky up and down or back and forth, so that the motion of your hand is perpendicular to the direction that the wave ends up traveling. So here the hand is moving up and down, the wave is traveling left to right. But individual particles within the spring only vibrate up and down as this wave is traveling. By contrast, a longitudinal wave is one where the disturbance is parallel to the direction of the travel of the wave. So if you again have a stretched out spring, you can move your hand back and forth parallel to the direction of the spring, and you'll create compressed regions and stretched regions of spring that travel down the length of the spring. As they're doing so, a particle that is part of the spring will oscillate back and forth parallel to the direction of travel of the wave, but it will still remain generally localized and return to its exact location after the wave has passed through. There are other more complicated kinds of waves. For example, water waves are in fact a combination of transverse and longitudinal waves, and if you track the motion of a water particle, that water particle would actually travel in a circular fashion, so it has both motion that is perpendicular to the direction of the wave travel and motion that is parallel to the direction of the wave travel. And in turn, that makes actually water waves more complicated to think about than other types of waves, so we will actually limit our study to waves that are one type or the other, or dominantly one type or the other, instead of something as complicated as a water wave. So, all waves have some characteristics that we can use to describe them. First of all, you have to have some sort of periodic motion, and simple harmonic motion, which you may have studied in your Physics 1 class, is an example of a type of periodic motion. So if you have an object that is in simple harmonic motion or some other form of periodic motion, that can produce waves, and waves share many of the same characteristics with each other. For example, they all have an amplitude, and the amplitude is what we call the maximum displacement of a particle of the medium from its equilibrium position. And you can have an amplitude for a transverse or a longitudinal wave. It's the furthest a particle moves from its regular quote-unquote position as the wave passes through that medium. The wavelength is the horizontal length of one cycle of the wave. The period is the amount of time it takes for one cycle of the wave to pass one point that an observer is located at. And the frequency is the number of cycles of a wave per time period. Well, if the period is the length of time per cycle, the frequency is the number of cycles per time, you can deduce that frequency and period are inverses of one another. So we generally use a script F to stand for the frequency and a capital T to represent the period, the length of time for one wave cycle. They are inverses of one another. Furthermore, we can deduce how to calculate the speed of a wave. Speed, you'll recall from Physics 1, is distance over time. The distance that you could use, you could observe, well, the distance of one wave cycle would be the wavelength of that. We use the Greek letter lambda to stand for wavelength. Over the time, well, one period, or one rather wavelength of the wave will pass an observer in one period of time. So the distance would be one wavelength over one period of time. So you could write wavelength over period, or using the fact that period and frequency are inverses, the speed could be rewritten as the wavelength times the frequency. So here's a visual representation of what's going on. Again, if we have this hand shaking the spring, we're creating waves that are traveling down the spring. And you could plot the vertical position of the slinky as a function of distance. In other words, essentially a snapshot of what the spring looks like after you have a series of pulses traveling down that spring. And if you did so, then from that graph you could directly measure the wavelength. You just pick a point on a wave cycle and measure until you get to the same point on the next wave cycle. That, by definition, is one wavelength of the wave. You could also, from this, measure the amplitude, because you would have the maximum disturbance from the equilibrium position, and that would be the amplitude. The amplitude, importantly, is not trough to peak, it's equilibrium to peak, or equilibrium excuse me, to trough. But it is also a distance. You could, however, sit and watch the spring just at one particular location. So imagine that you just watch the spring where this red dot is in the part C of the diagram. Well, you would also see the spring bouncing up and down at that point. So if you graphed the vertical position of the slinky as a function of time, you would get a very similar pattern in terms of the graph. But if you're plotting it versus time, you can't actually deduce what the wavelength is. Instead, you can deduce what the period is, the length of time it takes to go from one part of a wave cycle to another part of the wave cycle. You can deduce the amplitude because you're still thinking about the vertical position of one point on the slinky. But you can't read wavelength off of a time graph, and you can't read period off of a distance graph. So let's do a few conceptual questions. Again, I would encourage you to pause the presentation and see if you can guess the answer before listening to my response. If we looked at this graph waveform, what is its period? Half a second, 1 second, 2 seconds, 4 seconds, or we do not have enough information to deduce this? The answer is about 2 seconds. Again, this from equilibrium to maximum positive position to equilibrium to maximum negative position to back to equilibrium is one full wave cycle, and the period is the amount of time it takes to complete one full wave cycle, and the graph tells us that that period is 2 seconds. Here's another one. If we look at the same waveform, what is its speed? And the answer to this is there's not enough information to determine this. On this graph of wave displacement as a function of time, you could deduce what the period of the wave is, so that's the 2 seconds. But you would also need to know something about the wavelength of the wave, and you are not given any information that would tell you what the wavelength of the wave is in this particular situation. So the wave speed could not be deduced from the information on this graph alone. How about if we tell you the wavelength of a wave is 10 meters, what is the speed of the wave? Is it 1 meter a second, just under 7 meters a second, about 10 meters a second, 15 meters a second, or there's not enough information to determine? Well, the wave speed is the wavelength divided by the period, and if I have 1.5 oscillations in 1 second, that means it takes about 2/3 of a second for one oscillation. So the period of this oscillation is about 2/3 of a second. If you take the wavelength, which is the distance the wave travels in one oscillation, 10 meters, divided by the period of the wave, 2/3 of a second. 10 divided by 2/3 gives you about 15, and so the answer here is 15 meters per second. So, when we play around with making waves on a spring or a string, you should observe a few things. There are some factors that you can change that don't seem to affect the speed of the wave, and they include the shape of the pulse that you have. So square, triangular, round, what have you. The amplitude of the pulse, how high the pulse is above equilibrium, doesn't seem to control the wave speed. How wide the pulse is, same measure. I'm not sure if this movie will show up very well in the online recording, but it shows two pulses on actual springs being recorded on video. And so if we play that video, let me see if it'll let me walk through it step by step. Apparently not. Well, we'll try. So they start out here, and here come the pulses. And you'll notice the pulse on top is slightly ahead of the pulse on the bottom. It's a much taller pulse, even though the pulses are of about the same width. And as they travel across the screen, they stay the same relative position to each other. And when you get to the other side of the screen, the top pulse is still ahead of the bottom pulse slightly, but they're traveling the same speed as they travel across this medium. There are factors that do in fact influence the speed of the wave, and hopefully you found this in your explorations. If you stretch the spring tighter or let go of some of the tension in the spring, that affects the speed of a wave traveling on that spring. And you couldn't change this in the exploration, but it turns out what the spring is made of and how massive that is matters as well. So the mass density, which is the mass per length, since we treat a spring as a one-dimensional system, also influences the speed of a wave. All right, so a couple of questions. If you think about tension in a string or spring, how would changing the tension change the wave speed? Does increasing the tension increase the wave speed or decrease the wave speed? And the correct answer is increasing the tension increases the wave speed. Again, hopefully you observed in your explorations that when you pull the spring so it's more taut, which is an increase in the tension in the spring, waves travel faster through that material. How about the mass density? You didn't change this in the exploration, but think about it for a moment and make a prediction. If you increased the mass density, so you made more mass per unit length of the spring, would that increase or decrease the wave speed? Turns out that increasing the mass density decreases the wave speed. One way you can think about this is if you put more mass in the spring, it has more inertia, it's more resistant to changes in its motion, and that overall results in a slower wave speed as the wave propagates down a string or a spring. In fact, and we're going to go beyond what we can prove at this point, it can be shown that the speed of a wave on a string or spring is equal to the square root of the tension on that string or spring divided by mu, and here we're using mu to represent the mass density of the string or spring. It would be the mass per length of that object. So here's a sample problem to help us work with that concept. I don't know if you ever made a tin can telephone when you were a kid or last week, but here a brother and sister try to communicate with a string tied between two tin cans. If you've not done it, by the way, that's how you do it. You tie a string between two cans, poke a little hole in the bottom of each can, and if the thing is stretched out so the string is taut, you can actually relay messages down the string between the cans. If the string is 9.5 meters long and has a mass of 32 grams and it's pulled taut with a tension of 8.6 newtons, how long does it take a wave to travel from one end of this string to the other? Well, wave speed, we've just said, is equal to the square root of the tension divided by the linear mass density, or if you prefer symbols, the tension I'm calling F, the mass density we use mu to represent. Let's find the speed of the wave based on this information. So 8.6 newtons, we're told, is the tension. The string has a mass of 32 grams, so that's 0.032 kilograms. It is 9.5 meters long. If you put all those numbers together and take the square root, you get about 50 meters per second for the speed of the wave. Now you go back to what you know from Physics 1. If something is traveling 50.5 meters per second, how long does it take it to travel 9.5 meters? Well, if speed is, by definition, distance per time, time is distance over speed, you plug in the 9.5 meters and the 50.5 meters per second, and you get just under 0.2 of a second, 0.19 seconds. Another question involving wave parts and how they relate to each other. A 5.5 hertz wave. Hertz is the symbol of frequency. It's the same as saying 1 over seconds or cycles per second. So a 5.5 hertz wave is made by something that is oscillating back and forth 5.5 oscillations per second. So this wave has an amplitude of 14 centimeters and a wavelength of 27 centimeters, and it travels along a stretched string. So we're asked to sketch the wave and label its characteristics, deduce how far the peak on the wave travels in the time interval of half a second, and how far a knot on the string travels in the same time interval. So let's take those one at a time. Here's my little sketch of a wave. If I tie my string to the wall and then I'm over here shaking it up and down, I'll make this series of wave pulses that travels toward the wall. The wavelength could be labeled on here. It would be the peak to peak distance, 27 centimeters. The amplitude could be labeled as well, the equilibrium to peak distance, which is 14 centimeters. But the frequency couldn't be labeled on here, nor could the period, because this is imagined to be a picture of wave position as a function of wave displacement, rather, as a function of position. I would have to sketch a graph of wave displacement as a function of time if I wanted to label the period on that wave. All right, we're asked to deduce what its waves, well, actually we're not. We're asked to find how far the wave travels in half a second, but to do that we're going to need to know the wave speed. The wave speed for any wave that you know the frequency and wavelength of can be found by multiplying those two factors together. So frequency times wavelength, that's 5.5 cycles per second, a wavelength of 27 centimeters, and that means it's traveling 148.5 centimeters each second. If it is doing so for half a second, we can again say the distance that it traveled is equal to the speed times the time. That's 148.5 centimeters a second for half a second, and that works out to be 74.25 centimeters. How far does a knot on the string travel, though? Well, in order to deduce that, we have to realize that if you have a knot on the string, in one wave cycle, it travels up to the maximum displacement, back down to equilibrium, down to the minimum position, back up to equilibrium. So during one wave cycle, a knot on the string travels a distance of 4 times the amplitude. And so we're going to use that fact. The knot would move up and down 56 centimeters in each wave cycle. Goes up 14, down 14, down 14, back up 14. And so the question becomes, how many wave cycles pass in a given amount of time? Well, the frequency tells us that there are 5.5 cycles per second. And so that means in half a second, there are 2.75 cycles of the wave passing some observation point. And 2.75 cycles times 56 centimeters of knot movement per cycle gives you a net displacement of a knot on the string of 154 centimeters. Finally, a brief mention about reflections of waves when we make them on springs or strings. It turns out, and hopefully again you observed this in your exploratory lab, that when you send a pulse on a spring that has a fixed end, in other words, an end that can't move, that pulse comes in, hits the fixed end, and it gets reflected away from the wall, but it has been inverted or reflected about the equilibrium position. So if you send the pulse in above equilibrium, it will get reflected back below equilibrium. Similarly, if you send it in below equilibrium, it will be reflected above equilibrium. But when you have wave pulses on strings that have free ends, and the way you can do this with our springs is to put them around a rod from the lab so that you allow the end of the spring to move and slide back and forth. What we observe is when there's a free end, in other words, the end is free to move. I guess it's not entirely free, it's still held here in position, but it can slide up and down freely, that a pulse coming in above equilibrium gets reflected also above equilibrium. And this is a fact that we will work on in the next tutorial with understanding a model that would predict this behavior. And it's something that we will return to when we observe the behavior of light traveling through different materials, because this helps us explain some of the features of wave interference when wave travels through a series of different materials. But more on that in a few days. So this concludes the online lecture on waves and wave reflection. Hopefully this was a useful resource for those of you that are watching this. And if you've noticed any errors in the presentation, please as always let me know about those. Thanks.